It's my pleasure now to welcome our last keynote speaker of the day, Ruslan Salakhutdinov, who will be speaking about multimodal AI agents. Russ is the VP of Research, Gen AI at Meta, and professor at the Carnegie Mellon University. Russ Salakhutdinov earned his PhD in computer science from the University of Toronto under the supervision of our very own Nobel laureate, Geoffrey Hinton. After completing a postdoctoral fellowship at MIT, Russ joined the University of Toronto before moving to Carnegie Mellon University, where he remains. He also served as Director of AI Research at Apple and is currently the VP of Research at Meta. Russ's research focuses on deep learning, machine learning, and generative AI. He is an action editor at the JMLR, has served on senior program committees at top conferences. He has published over 250 research papers, and his work has received over 200,000 citations, according to Google Scholar. That's probably out of date already. He is an Alfred P. Sloan Research Fellow, Microsoft Research Fellow, a recipient of the Early Researcher Award from Ontario, Google Faculty Award winner, and NVIDIA Pioneers of AI Award. Please welcome Dr. Salakhutdinov.
Thank you. Is it, mic is up? Yeah. Thanks, Daniel, for the introduction. I've known Daniel for like 15 years now, since my postdoc days at MIT. Great. So today I'm going to talk about multimodal autonomous AI agents. I think that's the topic that's very important. I think something that I'm very much interested in. There's a lot of work happening in industry and academia on that topic. So I'd like to, show you what we've been working on. Everyone knows about large language models, right? There's been a lot of work in context learning, word knowledge, zero-shot abilities, remarkable advances we've seen in the last few years, right? But I do think that the next generation of these models is going to move beyond sort of chat interface, where I give you a question, I ask you the question, you give me the answer, more towards systems that can actually act on your behalf. And a lot of tasks, a lot of productive tasks that we perform today in the computer could potentially be automated by machines, right? And there's a lot of opportunities to automate some of the laborious tasks and also augment human capabilities. For example, how many of you have tried setting up AW instance? Right? It's a pretty hard thing to do. My students always complain about this. Why can't we have an agent that goes and does it on your behalf, right? Another example, can we create a set of PowerPoint slides to present the content of the paper? I'm going to talk about a couple of papers today. Would be great if I had an agent that would just read my papers and create a PowerPoint for me, right? Right now, mostly students do that for me, but it would be great if there was an AI that would do it for me. And today, I'm going to be focusing on web agents, right? Specific topic, just to make it a little bit more precise. So you can think of the systems where you have some visual encoding of the environment, say web pages, you have some form of text understanding, and then that goes to the web grounding, trying to understand what you're seeing on the web so that you can act on the web. And just to show there's been a lot of work in that domain. It's a very flourishing field right now. A lot of work happening in that domain. But let me show you a particular example, right, of what that technology could do. These are very cherry-picked examples. The systems are not working at that level yet, but imagine I ask the system to say, navigate me to a page of a good Thai restaurant in Pittsburgh. It should have at least 200 reviews, 4.4 stars, and pick the one with the highest rating, okay? Now, if I give that task to the agent, here's what the agent can do, right? It goes on Yelp. It's essentially thinking, searching for Thai restaurants. It's all done autonomously, right? No human involvement. It sort of finds, the restaurants, it sorts them according to the ranking, it checks the constraints, and then comes up with this restaurant, which actually is a pretty good restaurant in Pittsburgh, right? So that's done. I can ask it to say, well, make a reservation for 2 people, use my name, JY, is a student who built the system, and use the phone number. The model goes on Google, tries to find this particular place, picks up a date, makes a mistake. I'm asking it to do lunch. It actually does dinner for me. And then it sort of, fits the phone number, gives me the phone number, and then, stops because you need to get a confirmation, right? Again, all done fully autonomously. Or I can ask it fun things, like help me navigate to a shirt that has this on it. right? So it's sort of understanding the visual understanding of what the task is, and then you go to Amazon, you try to find something like this, and then eventually you find actually a T-shirt with that logo on it, right? So again, this is something that you could sort of see the future of agentic abilities, where the model actually smart enough to go find the right information, submit your forms, and actually act on your behalf. So we've been building this environment that we call VisualWebArena, which is the way for us to try to evaluate how good these models are, right, and where we are today. We designed a lot of these visually grounding tasks and try to come up with some realistic tasks that we can test existing systems. So there's 3 environments: one-stop shop, which is basically mimics Amazon; Reddit, which is the forum environment; and OS class, which essentially mimics something like Craigslist, right? And let me show you what these environments look like. So let's say I give you the task. I ask you to find this bike. I give a picture of my bike. I want it to be between $300 and $500, and I want to make a comment offering $10 less than the asking price, okay? So the system essentially has to navigate to the bike category. And again, this is all has to be done autonomously, find that particular bike, and then make a comment. And very soon you'll start having systems that will basically negotiate on your behalf, right, the price. And there's probably going to be an agent on the other side negotiating on behalf of the seller. Here's another example, just to show you how the complexity of these tasks. Buy me this cheapest printer and send it to Emily's place, as shown in the image. And notice that the image is upside down, right? So we count this as sort of, the model has to understand that the image is upside down, has to rotate, figure out what the address is. And this is what the system needs to do. It sort of has to understand what it's looking for, clicking, going through stages, and filling up the forms, based on the address, and then actually placing the order, right? There's another task just wanted to show you, an interesting task. This is a visually grounded task. If I ask you what's the 2022 total nominal GDP of the area that produced the most sugarcane in the year of 2021, I kind of have to look at this image, and I have to understand that the year 2021, I think Asia here produced more sugarcane than Brazil, right? So I kind of have to look at the graphics and really understand what I'm seeing on the graph here. And then, once I analyze what I'm seeing, this is what human would do. You kind of go on Wikipedia, and then you find the answer, right? So it's sort of the tasks that some of the tasks are easy, some of the tasks are actually pretty hard. And the way I can set up this environment is that for people who are working in the space of reinforcement learning and MDP, markup decision process systems, you can formulate it as a POMDP problem. You can say, well, there's an environment. You have observations of the environment. This could be images of web pages in this case, could be HTML. There's something that's called accessibility tree, which is simplified representation of HTML. You have a set of actions. And what's interesting about these environments is that the action space, is fairly diverse. Certain actions are discrete, like clicking on a particular element. Certain things are continuous. You have to type in a particular element specific text. And it allows you to sort of mimic what humans would do on the web. You have a transition function in this case. You can think of it given the state, and you take the action. The system actually transitions you to the next state, which is the next web page. And you have a reward function that's telling you how good you are in terms of solving these tasks. Like if I give you the task, have you solved it or not, all right? And so, I can go into more details, but it's nice thing about these environments is that if you're doing research in reinforcement learning domains or like in MDP domain, a lot of algorithms do translate into these more complex environments. When we looked at the tasks that we've created, this is something that I've created at CMU, we sort of see the distribution of tasks where we look at the visual difficulty, trying to understand what the system is asking, versus reasoning difficulty, how many steps you actually need to execute to solve the task. And it's interesting to see that about 15% of the tasks are pretty easy, right? You need to do a few things to solve the tasks, but quite a few tasks are actually pretty difficult. So how do we solve these systems, right? And then we also have a reward function, and you can think of reward function as a way for us to verify, have you solved the task or not, right? This is something that we've designed, generally very difficult to do up in the real world or on the real web. But if I ask you a particular question, what is the ISIN number of the company and so forth, and there is an exact match. Or if I say it's something like this, what this man is wearing to my wish list, then I'm basically evaluating based on visual question answering. I'm asking like, is this a polo shirt, is this a green shirt, and such. So we have a sort of a proxy way of evaluating like, have you successfully solved the task? Right? Now, when we look at large language models, so what we call visual language model agents, we can think of multiple things, right? A lot of work that's happening right now is that we look at something like HTML accessibility tree, which is one way of looking at the data. But the other more interesting way of looking at the data is actually looking at the visual representation. And the representation that we call a set of marks-based representation, which basically is telling us what are clickable elements or what interactable elements in the environment you can interact with. So how does this work? Let's say I give you the goal. I'm trying to find this post, navigate into the comment section of it. I have some representation. This is a mock-up of the Reddit environment. I have my set of marks representations telling me which elements I can interact with. I have some textual representation of the environment. That goes to the multimodal large language model. And then the multimodal large language model is what it outputs what's called chain of thought, which is the reasoning step of what the model is trying to do. So it says, well, let's think step by step. The objective is to navigate to find a particular post and so forth. In summary, the next action I will take is click on element ID 34. So it's actually, figuring out where exactly you need to click, right? So there is a little bit of reasoning, what the task you're trying to solve, as well as very good visual grounding. So understanding what you're actually looking at and what you need to interact with. And then the action is you take a particular action and then you proceed. We've tried analyzing this model to try to see, where the current systems are. So if we only rely on text, HTML, we hit about like 10% accuracy. This is a GPT-4o model. If we look at text plus captions, we look at multimodal, we look at set of marks, we kind of like hit maybe about 18% of the tasks, right? When we look at the human performance, we hit about 90% of these tasks can be solved by humans executing it. Now, these sort of master students at CMU who are executing those tasks, we asked them to do that. We gave them free pizzas to sort of do that. And the results were staggering. Like a lot of things humans can solve, machines cannot, right? So there's a big gap, interesting gap to look at. One interesting thing that we found is that humans do make mistakes, right? There's like about 10% of the tasks they couldn't solve. So we were curious about what are those tasks, and just interestingly, we found out humans are not very good at information extraction tasks. Because what ends up happening is that we're asking somebody to say, hey, find me the bike, between these prices, get me the best one, the best price. And what humans tend to do, you kind of like look through it, you find one bike, you find the second bike, and you say, I'm not going to spend more time looking for the rest of the bikes. It's done. Like, this is the one that I'm going to get. Whereas there's 10 other bikes, right, that you could actually find a better deal. So those are the mistakes that humans are doing, and this is where we believe agents will be far more advanced than in terms of information extraction style of tasks. Here's an example. This is a cherry-picked example. It's a kind of interesting one. You give it an image, and you say, I don't like the author of this image. Can you help me block them, right? And it's not like we've trained the model on these tasks of saying, like, here's how you block somebody on Reddit, as an example, right? The model actually tries to get its knowledge and understand what the process should be and executes a series of tasks to accomplish this. Now, in terms of when we built this environment, we do believe that it's a step towards building these general purpose agents, but the tasks are not very consequential. We kind of like trying to understand, what we can do with these tasks, but the tasks are simpler, and even current models do not even do well on these problems, right? And obviously, the long-term goal is to automate some of these, some of these economically valuable tasks. In terms of where the model fails, right, from the abilities, they do fail from long horizon reasoning and planning. So for example, a lot of times what the model would do, it would actually try to solve the task and then undo it and basically say, I can't solve it. A lot of times agents tend to stop exploration and execution early, so you're trying to do something and then you stop and you say, I don't know what to do next, right? And we need a lot, to close the gap, we need to do a lot more work in this space. Obviously, reasoning and planning over long horizons is a sort of fundamental problem in in decision making, in reinforcement learning domains. We also found that allowing agents to search, to execute some form of coordinate search in parallel and ask for clarification questions would be the key to actually getting these systems to work. There's a lot of work right now on what's called test time inference, and you can think of search as one way of doing it. And we also need strong visual language and coding models, and also identifying appropriate level of abstraction. There's a lot of work right now happening, again, in industry, in academia, of trying to figure out at what point you call tools that can solve things for you, at what point you call these general systems that can take over your computer and execute tasks on your behalf, and what that combination is. Early versions of this, as you're seeing with OpenAI's deep research and Google, and you'll see more and more of that technology coming online. Now, one interesting thing about this domain is that you have this notion of exponential error compounding in agents, right? So typically in chat-like systems, I ask the question, you give me the answer, and if the answer is okay, that's good. When we think of these agentic capabilities is that, if I'm correct 90% of taking every single action or every single step, if I'm trying to execute something that requires 10 steps, 30 steps, my success rate goes down significantly, right? And this is one of the drawbacks of these models where, you have to reach the point where you're like extremely accurate in terms of the ability for you to explore and take the right set of actions. And that's fairly challenging to do. And so there is a fear in the community with these models. Are we in the same sort of ballpark which what happened with self-driving cars, right? With self-driving cars, we went very quickly from 0 to like 80%. And after that, the progress basically stalled. Going to like 90%, going to 99% is like extremely difficult to find all the corner cases. Now, when we think about these models, you can think of them as local decisions. Decisions that you're making right now have global consequences, all right? As an example, let's say I ask you, add coconut milk to my cart. Again, it's a simplistic environment. Well, there are multiple actions I can take in this environment. I can click on a particular element, and then I get to the next state, or I can click on another element, I get to the next state. So I take an action, gives me the next state. I take another action, gives me another state, right? And so forth. And you can think of it as sort of like a tree branching, and you have an exponential number of possibilities that you need to explore, right? So all of these lead to particular outcomes. And let's say this is the right outcome, and the probability of taking this action is 0.1, right? And the probability of taking this action is 0.5. That's your current model. You can think of it as a policy that's telling you what action you need to take. And so it's very hard, if your base model doesn't kind of make the right decisions early, chances of you succeeding becomes fairly small. And so what can you do in this case? Well, one thing you can do, which is a very naive approach, is to do search by repeated sampling, okay? So you sample actions from the language model, from your current model, until you have a stop action, which the model says, I've solved the task, right? And let's say you sample this, you evaluate the resulting trajectory, you look at the resulting trajectory and say, have you solved the task, have you not solved the task? And then maybe you didn't solve the task, and then you repeat, right? This is a naive form of what's called rejection sampling, right? And the remarkable thing about rejection sampling, I think that many of you probably have heard it's a very basic statistics sort of thing that you learn in your statistics 101 class. But what's remarkable about this idea is that this rejection sampling is basically the driver of pretty much all of the reasoning models that we have today. I don't know how many of you played with O1, O3 style of models. These are models that can actually reason, solve complex math problems. They're all essentially relying on rejection sampling, right? With a scaled up version. So a lot of times you generate samples, you know whether you've succeeded or not, and you repeat. And then you use those samples to actually do hill climbing. So it's a fairly powerful idea, and then you do this rejection sampling up until maybe you solve the problem. And it turns out that rejection sampling does help. We found it in our environment, that if you actually repeat it multiple times, the numbers do go up. Now, the space is exponentially large, right? So can we guide the exploration? And again, the key idea here is to use some form of value function and apply the value function to intermediate states. These ideas have been around for decades in computer science, in statistics, and so there's nothing particularly new here, but it does sort of point to the point. It does point us to this setting where, even with these complex environments, try to figure out what the right value function to use so that you have more guided search for the answers. It becomes very important. So how do we do this? Here's a very simple algorithm, right? You have a baseline agent that proposes actions. So the agent that takes specific actions in the environment. You have a way of backtracking in the environment. So you basically have to say, well, if I take the wrong action, I need to be able to backtrack. Right? Creates a certain set of problems, but we'll come to them later. So let's say you can backtrack. So if you took the wrong actions, you can always go back. And then you have a value function. And you can think of the value function is essentially an estimator of the probability of success. So think of it as a number between 0 and 1. It's basically telling you, if you take this action, are you going to succeed or not? How good that action is. And you assign the value to each state, and you say, well, the second state is better than the first state, so I'm going to proceed with that. And in this work, we're actually using multimodal LLM and 4o that acts as an evaluator. There's a common technique right now that people are essentially using LLM as a judge, right? So you're giving the full trajectory to the model and say, hey, is this a good trajectory? Is this not a good trajectory? It has its own disadvantages. Ultimately, you want to build your own value functions, but it turns out that it's much easier for the model to say, yes, this trajectory looks correct and this trajectory doesn't look correct, as opposed to building these models yourself. I'll come back to that later. And so here's how the procedure sort of works. You give it an instruction. Can you add this and other canned fruit to the same brand that looks like this? And I give it a picture. But red instead of brown to the comparison page. And if you're actually doing search, you can sample multiple trajectories, right? You pick the best one according to the value that you get. And at some point, you sort of do this greedy decoding, and you proceed up until you actually solve the task, right? This is a very sort of naive notion of test time inference techniques where you're actually spending a lot more time at test time to figure out what the right outcome should be, right? And there is a lot of work on using these Monte Carlo sort of rollouts, figuring out what the right value functions should be. If any of you have heard about the game of Go and how they sort of built the AlphaGo, that's essentially what's happening in these domains as well. And if we look at the results, there is something that's called WebArena, which is sort of a similar environment. If you look at Llama or GPT, you sort of have these improvements. VisualWebArena is something that we were looking at. Again, with search, you have substantial improvements. Not far enough to reach human-level performance, but it actually does tend to solve certain tasks. Like a lot of tasks that we found that we can actually solve is that, we ask the model to buy a blue shirt. The model goes and ends up on the web page with black shirts. Comes back to me and says, there's no blue shirts, I'm done, can't solve the task, right? And what actually happened is that, you certainly took a certain action in your trajectory, so if you sort of go back and choose the right color, then you will get the right answer, right? It's a toyish representation of this. Having good value function is essential, and that's where, you'll see a lot of industrial labs are trying to figure out how do we build these large value functions that actually telling us whether certain steps that we're taking online or whether we're calling certain tools are, whether they're good or bad. And of course, there's still a lot of headroom for improving both the base policy in terms of the existing models and the value function, right? And we can kind of like see success rate versus search budget. As we search more, success goes up, right? But we need to spend more compute in order to be able to climb on this benchmark. Here's one example. I like this example. I would love if you have something like this where you take a picture and you say, hey, I want something like this in my apartment, add it to my wish list, right? The model goes on Amazon, finds this exact item, figures out what it is, and sort of tells you, like, this is what you're looking for. Do you want me to buy it for you? And then I go buy it, right, as an example. Or, like, I recall seeing this exact item on the site, help me find the most recent post on it, right? I recall seeing it in these sections. And the model sort of goes and tries to find that particular item and just navigates you to that setting. Now, the current work, you can think of it as, obviously search as a policy improvement function. That's what people tend to do. That's how we have these amazing reasoning models, like a 103. A lot of them, what they do is they essentially do rejection sampling. They find the right trajectory, reasoning trajectory, to get the right answer. They take this trajectory and they use reinforcement learning to say reinforce that trajectory and de-reinforce wrong trajectories, right? Fairly simple mathematically, but a lot of engineering effort. Improving value function by fine-tuning instead of prompting, right? Instead of using LLM as a judge, building your own value function actually looks at the environment and it's telling you that, oh, I think this action, you'll have more success reaching your outcome than taking this other action. Of course, exploring trade-off between improving the base agent versus doing more search at inference time. There is a big debate right now as to how much we can push on our base models, how accurate they can be, versus how much do I want to spend time at inference, like thinking or doing search, figuring out like what the right outcome should be. One interesting thing about the web in particular is dealing with destructive actions. Turns out that, a lot of things on the real web is very difficult to do, all right? And a lot of them are difficult to undo. You can't order an item and then say, go back, right, to the previous state. Is there certain things you can't also do on the real web? It turns out one of my students tried and got blocked, which is you can't go on booking.com or like on united.com and say, hey, let my agent learn how to book a flight. And then my agent starts like booking flights from Pittsburgh to Toronto, and then at some point, the United says, wow, there's a lot of demand for people flying from Pittsburgh to Toronto. Maybe the prices should go up, right? So there's certain things you can do online, and that actually creates a problem, right? How do we build a perfect simulator of the environment, like a web environment? And also, how can we collect the data at scale? And one interesting aspect, just the last thing I want to mention, is that these sort of agentic capabilities, they suffer from the data problem. Right, a lot of data, a lot of times we get this data offline and then maybe deploy them in the real world. So the question is, can we generate synthetic data and train our models? This is something that's fairly interesting research. It's at very early stages, primarily because it's very difficult to go online and say, hey, give me tasks of people solving certain problems, right? Give me the right trajectories. It's very difficult to get that. And so we've been sort of thinking about these ideas of LLMs generating tasks, verifying these tasks on live websites, and then evaluating whether you actually solve the task or not. There's certain environments like this. Just wanted to show you this is completely done by the model. It's a synthetic data. So it comes up with a task, find me the opening hours of this specific, and so it gives me the environment. So it came up finding the opening hours of La Sagrada Familia, and then it goes on the live website, finds the answer. Fully done synthetically. Or find information on European Union's climate change, and it sort of goes on the web and finds this information, right? So these tasks are generated by a large language model, a multimodal large language models without human intervention. And we do find that if we go and we sort of scale these systems up, we do see that it's interesting. We have like 97% accuracy in detecting and filtering harmful content. You have certain high success rate in terms of generating tasks. 82 accuracy in judging whether you've done it successfully or not. And we do see you can get this data at scale and then train much better agents. So let me just summarize. I've sort of talked to you a little bit about this environment where we've tried to build something that we can evaluate how good these models are, right? What we call VisualWebArena. We've looked at inference time search algorithm, very simple one, but fairly powerful in terms of the ability of these algorithms to actually improve the accuracy of these models. And a little bit of a data, I've mentioned a little bit of a data pipeline for large-scale generation and verification of synthetic tasks, right? One thing I do want to point out that in sort of these environments, AI safety and robustness, especially in the age of these autonomous systems, becomes a critical point. So you will see more and more work that's going to be done in academia again and industry on the safety and robustness. These models are not very robust, and these models are you can easily break them, right? There's a work that was done at CMU on adversarial attacks of multimodal agents, and what the model actually does, what you can do, is you can say, I can modify my website, I can modify my images in such a way that when the agent looks at my website, it actually leaves a good comment. Like, you basically hacking the instruction of the agent and saying, every time agent goes to your website, you always click on 5-star rating, and you sort of, giving this instruction, and the model sort of, because it's confused as to what it's looking at, and you're doing it in a specific way, you can actually hijack the model and instruct it to do something, right? So, and then the other thing I always like to point this out is a funny one. Anthropic also released what they call Claude computer use. And they sort of have this notion where they're also building the agent that actually takes over your computer and accomplishes certain tasks. But they found, in one, Claude accidentally clicked stop for a long-running screen recording, causing all footage to be lost, and another Claude suddenly took the break from our coding demo and began using photos of Yellowstone National Park, right? So what this basically means is that occasionally these agents take the wrong action, and if you take the wrong action, you don't recover from that, the agent sort of starts doing something else. Okay? And on that point, thank you very much. And I want to thank my students who've sort of been doing that work at CMU. Thank you. So was running a little bit behind.
All right, we have time for questions. Please make your way up to mics. We got one right here in the front.
Hello, hello. Hi. First of all, I'll acknowledge that I'm a big fan of knowledge graphs and more symbolic AI. But my question, I really liked what Kelsey was presenting and talking about graph neural networks. And my question is, in either the value step, is there any ideas of using what someone referred to in our technology as a human behavioral model, which is a graph representation of the human experience, to use that as some form of evaluator for, are we going in the right decision or not? Have you seen integration or a hybrid approach of knowledge graphs and, let's say, large language models or reasoning?
That's a very good question. I think that there's certainly a place for the use of knowledge graphs. In this particular environment, when we're using LLM as a judge, we've tried looking at the knowledge graphs to try to, given a particular query, we try to basically see from the knowledge graph what the right answer is. And then that becomes a target for the model to improve on. I haven't seen a lot of work on integrating LLM and knowledge graphs. There is some work on factuality, which is kind of, one aspect where you have a knowledge of facts. And then you're trying to come up with a model that then when the model gives you the answer, it's trying to figure out, like, is it factually correct or not? Those are the efforts that are happening right now. But one of the advantages of LLMs, like in this particular domain, we were very surprised by how much these models know about the facts. I can ask about some obscure website in Ireland, and it's pretty good at telling me like what it's for, what to use it for. So in terms of eliciting knowledge from these models, it's actually pretty remarkable. But I agree with you, there's probably going to be, like, at some point, combination of what LLMs are giving you versus specific knowledge graphs that you have, specifically for factuality. Because the web, a lot of times, things that you see on the web are not factually correct, and you have to be very careful how you process that data.
All right, we got another question here. Russ, if you could repeat the question after.
Oh, yeah, sorry.
Excellent. So thank you very much for the talk. I'm curious what you think is the right interface for agents to be taking actions on the web. Specifically, it seems like many of the technical problems you allude to, such as rollouts and all that, could be resolved if, as you said, the interface is through API. And if you think API is the right interface for agents, how do you incentivize the entire internet to have agent-specific APIs?
Good question. So the question is, what's the right interface for the agents? Should it be done through APIs? And ultimately, if that's the case, how do we incentivize the entire world to actually convert to that? It's a very good question. My sort of belief right now is that the existing systems, if you have an API, let's say you have an API for Uber, right? You have an API, you might as well have your agent actually interact with the API. And that's where I think the future is going to be moving towards. The problem is that right now, APIs also have a lot of security risks to them. And so a lot of websites, a lot of companies do not want to open API to the outside world. And interacting with environments through the web is one way of doing it. So at least in the shorter term, I will see systems that are hybrid, that will call tools. Like, for example, if I'm searching for something, there is no reason for me to interface it through the web. I can just call Google search and get what I want. But ultimately, at least in the shorter term, it's going to be a hybrid. You will have systems that call APIs. If there is no API, they will get on the web and crawl the web to get the information that you need. A lot of times also, systems that should be smart enough to complete information on your behalf, right? It would be great. I was trying to sign up my kid to go to the swimming class. It took me like an hour to sign him up, because you go to this website, it's like very obscure. You have to fill information, you have to click on a bunch of things. You don't know where things are. Like, why can't my agent go and do it? Right? But at some point, the question, I guess, the longer term question, 20 years from now, what is the web going to look like? I think it's going to be very different from what it is now as we build these systems. And these systems will be interacting with the web as opposed to humans.
All right, we're going to take a question. We're going to take a question from online now.
Can you hear me? Recent LM reasoning research uses reinforcement learning, inference scaling, search. I wonder what your opinions are on whether the transformer architecture is fundamentally suitable for reasoning.
So I think that the architecture versus the reasoning, there's two separate questions, right? The way that the reasoning systems work today is, as you alluded to, is basically reinforcement learning, but very simplistic reinforcement learning, right? In a nutshell, it's just a rejection sampling. You're generating a lot of thinking tokens, and then you get the answer, and you verify the answer. And once you have those pieces in place, you can reinforce that. I do think there is some architectural challenges to be able to maybe perhaps have faster inference, where you're generating tokens, faster or in parallel. But I think that existing architectures for reasoning are probably pretty decent at this point. I don't see. There's some thinking about, do we want to go into embedding space? Do we want to have a world model? And these are all good questions. But what I'm seeing right now, at least in the shorter term, these reasoning models, at this point, is just a test time inference scale with RL and rejection sampling. So, absolutely. I mean, to your question, academia should be looking into this. There's always amazing new architectures to define.
We'll take another one from the room right here.
Hi, thanks for the great talk. So I think the thing that you said that most intrigued me was the idea that, okay, I'm going to send my agent out into the world to negotiate for me. On the other side is going to be an agent negotiating against me. So mostly I just wanted to hear you talk more about your thoughts on this, but maybe to qualify that, by analogy to AlphaGo or strategy games, like you're not just exploring a branching tree, you're exploring like a game tree that has an opponent, and you may need to model that opponent. So how do you think about modeling agentic behavior when you're designing an agent?
Yeah, very good question. I think that, so the question is, the agent negotiates on your behalf, and then somebody else is negotiating on somebody's behalf, and so it becomes like a multi-agent system. I do think that we are at the very early stages of this setting. I do think that multi-agent systems will take place. I do think that you're going to have your agent that's going to be your personal assistant. You're going to be executing things, and it's going to be interacting with other agents in the environment. I haven't seen successful stories yet in this setting, primarily because it's difficult to set it up, and it's very difficult to evaluate. That's one of the biggest problems that we're seeing today, being able to evaluate how good these models are. Because you need a good evaluation function to actually, train these models. But that's not my area of expertise, but I do think that we'll start seeing multi-agent interactions within Gen AI environment very soon. So it's an amazing area of research, I think.
Let's have another question from that side, please.
Thanks for the presentation. I'm curious to know when you said that the weaknesses of agent is in reasoning and also exploration. How about if we add WebGPT and line graph to them?
Sorry, can you repeat the last one? Like, so one of the key things. Sorry, let me just go back to, what was your exactly question? Sorry.
The weaknesses of agent you said compared to human is reasoning and also exploration.
Right.
How about if we add WebGPT and also line graph to them?
Yeah, that's a very good question. So, if you start adding like some of the reasoning models, right, how good it's going to be. If you start adding some of the LangChain kind of like, environments, that's a good question. I don't know, LangChain sort of, there was a lot of excitement early on. I don't see that excitement now, which probably means that they're not robust enough. In terms of reasoning, these models will get better. But what I'm seeing right now is that reasoning has been sort of pushed a lot on math, sort of domains or STEM domains where you have a verified answer. If I give you the question, I know what the right answer is. I can sample different reasoning trajectories to get to the right answer. With these environments, with agentic environments, it becomes much more difficult because they might not be the right answer. And so that becomes far more difficult where your reward model is not exactly, yes, you solved it or you didn't solve it, but it becomes more fuzzy, all right? Especially in the settings where I give you the task which is not precise. And the model has to kind of understand that the task that I'm giving you is not precise. So it has to follow up with clarifications and corrections. So I do see the future where it's going to be humans working with the agents together to solve some of these tasks.
Please, thank you. I have another question if there is not anyone.
Well, actually, we're running out of time. I want to make sure we have something of a break, and so I'm actually going to call the end of questions right now. I'm very sorry for any remaining questions there are. But let's thank Russ one more time.
Thank you.